In previous video, we have learned about how to design an arithmetic circuit. So we have learned about the inputs that is given as an input to the adder. So like carry in and mode select signals, that is S0 and S1 is there. Selection signals, selection input lines S0, S1. Then input A1 is there, which is fed directly to the X1. And a combinational circuit is designed for B1. So we make use of a K-map method in order to decide which all are the gates or the circuits, what is the circuit that is being used in order to give us an input to the full adder in place of this Y1. So if there is n bits, means n full adders will be arranged in a cascaded form to implement this arithmetic circuit. So this is the function table for the arithmetic circuit. Here we are having the selection inputs S1, S0, carry in. Based on this, you will be getting the Y value, not the Y value that is determined. And based on this four inputs, you will be getting the output F. Okay, so here if the S0 input is 0 and S1 is 0, the Y will be equal to 0. If S0 is 1 and S1 also equal to 0, Y will be equal to B. If S0 is 0 and S1 is equal to 1, then Y will be equal to B complement. If both the S0 and S1 they are 1, then the Y will be equal to all ones. This is how the Y value depends on this S1 signal, S1 and S0 that we have seen in the truth table earlier while deciding for this input B. Okay, so this is the truth table for the function table for the arithmetic circuit that we have designed here. And based on that, what is the output you will be getting? So if this is a combination, then F is equal to A. So what does it do? It transfers the content of A. And if there is a C is equal to 1, then A plus 1. And if S0 is equal to 1, and then Y equal to B, so F is equal to A plus B, add operation will be performed. Similar is the case with here, S0 equal to 1 and C is equal to 1 means it performs the output F is equal to A plus B plus 1. Next, if S1 is equal to 1, which means that the Y will be taking the complement of B complement. Function output will be A plus B complement. If S1 equal to 1 and C equal to 1, then F plus B complement plus 1, which is equal to 2's complement of B, which is added to A, and that is equivalent to A minus B. Then in this case, last that is S1 S0 equal to 1, but carry in is equal to 0 means F will be equal to A minus 1. If carry in is equal to 1, again it performs the transfer operation. So these are the different functions performed based on the selection inputs S1 and S0. Also, Cin also plays a major role in performing these operations. This table shows the effect of output carry. So this table shows the effect of the input carry, In this table, it shows the effect of output carry along with the inputs that is used for selecting the function S1, S0, Sn, Cin. Together with that, if Cout is equal to 1, then what it does? If Cout is equal to 1, in this case, it will be performing f is equal to a plus 1. F is equal to a plus 1. And that is a is equal to 2 raised to n minus 1. A will be equal to 2 raised to n minus 1. And f will be providing the output as 0. If Cout is equal to 1, f is equal to 0. If a is equal to 2 raised to n minus 1. So this is the effect of carry. What is the operation to be performed? That is a plus 1 is the operation performed. And if the Cout is equal to 1 means the resulting f will be equal to 0, which performs the operation that a will be equal to 2 raised to n minus 1. That is, you will be having some 1 that is, you will be having some output in which all the bits will be equal to 0. Okay. So if Cout is equal to 0, a will be 2 raised to n minus 1. Then if a is, in next case, if a is equal, Cout is equal to 1, 0, 1, 0. F is equal to a plus b, performs the operation f is equal to a plus b. So if Cout is equal to 1 means what it does is a plus b will be greater than or equal to 2 raised to n. 2 raised to n means if n is equal to 8, it is 256. If n is equal to 4 means 16. So a plus b, after computing the operation, it will be greater than that 2 raised to n, size of the bit. It will be greater than the size of the bit. In such case, overflow it occurs. And 0, 1, 1, in that case also, a plus b, it will be greater than or equal to 2 raised to n minus 1 if Cout is equal to 1. When does that Cout will be enabled? If an overflow is being occurred, or while performing the addition, if it exceeds that value, that time the Cout will be set to 1. So what are the cases and how it affects the arithmetic function that is being listed out in this table? Just go through it. Okay. Now next is based on the things that we have learned, we need to design any adder or subtractor circuit based on the requirements. So here one example is given. A selection variable S, with the help of a selection variable S, two inputs A and B. So we are having selection variable S, two inputs A and B, and it is defined that when S is equal to 0, it performs the operation A plus B. S is equal to 1, then the circuit should perform the operation A minus B. So for that, we will be having a adder. Okay, we will be having an adder, parallel adder. So two inputs will be given, A and B. So if S is equal to 0, just performs the operation A plus B. So giving the output as A plus B. So no additional combinational circuit is required. It will be giving the input to the, it will be giving the direct input to the X and Y to get the result as A plus B. But in case of S is equal to 1, what it does, again, You will be having a parallel ladder, x and y input. So you need to perform a minus b. So a directly can be given as an operand to the x. In case of b, what a minus b need to perform, isn't it? So this b, it need to have some combinational circuit. B will be given as an input to the combinational circuit, and then it is based on the output from the combinational circuit that will be given as an input to the Y to get the output A minus B. Okay, so we need to determine what is the combinational circuit that will be defined for this task. So for that, in order to perform the A minus B, you can do the operation like A plus B complement plus 1. Okay, in order to perform the A minus B, you can do this operation. So for that purpose, you can just draw the truth table and see. And that is so you can just see S1, S0. Oh, only one selection variable is there, isn't it? So only one selection variable is there, S. So based on the input AI and BI, if it is 0 means AI will be same as that of Xi. Okay, AI will be same as that of Xi. When you compare with the BI, if BI is 0, then YI is 0. If BI is 1, YI is also 1. BI is 0 again. So if from this table you can see that if S is equal to 0, then BI will be equal to YI. But if S is equal to 1, BI BI value will the complement of BI value will be making the value of YI. You can see like that. Okay, so based on that you need to draw the circuit. So from this itself we can understand that a NOT gate will be used here if S is equal to 1. So how it is being defined, how we come to this conclusion, we need to first find out the Boolean function based on this operation. So Boolean function can be found by first construct the functional table for this input, that is a parallel ladder. You need to first find the functional table. Based on the functional table, draw the K-map and you will be getting the Boolean function, and from the Boolean function you will be easily able to write the or design the circuit. So we can see that. So after plotting the K-map you will be getting like this, and you will be getting the Boolean function in this format. So based on this Boolean function, you will be able to understand that you have